Hello all, in today's video we're going to be talking about covalent bonds. And this is the counterpart, the other side of our two types of bonding that we've learned so far this semester. In the previous video you learned how to solve the electron configuration and the orbital diagram for a metal to nonmetal anionic bond interaction. Here we're going to be talking about covalent bonds. Covalent bonds are a little bit more tricky, and the reason they're tricky, one of the elements is not going to be donating electrons to the other element. What happens is we have this sharing of electrons going on. So it's a little bit more tricky to understand how this works. But the interactions between two different elements that are going to be sharing electrons follows a mathematical equation, which I'm not going to show you, but I'm going to show you the plot of this mathematical equation. So here we're going to have distance r. This is the distance between the nuclei. Okay? And on this side we're going to have the energy. The way that a covalent bonds interaction is going to work is kind of like if you put two spheres, two tennis balls, on the end of a spring. You can push the spring together, you can pull the spring apart, but there's a normal distance, a set distance, where there is no energy associated with it. So if I were to give these two tennis balls and squeeze them, we know the second I let my hands go, the tennis balls are going to go back to their original position. If I pull these tennis balls apart and let go, the second I let go, those tennis balls are going to go back to their normal position. Same thing happens with an atom. Let's say we have a H2 molecule. Two different hydrogen atoms, one with one proton, one with another proton, two electrons surrounding, one electron surrounding both. So there's a total of 2 electrons present here. So the interaction, this is going to be 0 energy. It actually becomes negative. It's called a Lennard-Jones potential. And what happens is it looks something like this. That is what the energy looks like for this interaction of hydrogen to hydrogen in a covalent bond. Now let's identify different parts on this plot to see what happens. The lowest energy, right here at the very bottom, is going to be just like our tennis ball example, where they're just at rest. There's no energy. You just have these tennis balls on the end of a spring, you set it on the counter, that is its normal standard state. Same thing is going to happen with these hydrogens. I'm going to draw it up here. We have the nuclei. We're going to have a sharing of electrons. The electrons are generally going to be in the middle somewhere, but it's a neutral position. There is no extra energy. The hydrogen molecule is happy being in this position. That is at the base, the very bottom of this plot. Now, as we move to the left, the distance between the nuclei are going to get smaller. So that is like taking our tennis balls and squishing them together. So over here, we're going to have nuclei very close together with electrons kind of around there, but the nuclei are extremely close together. Well, just like with a spring, if you keep compressing it, you have to keep putting in more and more and more and more and more energy. Well, in this instance, the protons will never be able to completely collapse on each other. So this energy of squeezing these nuclei together becomes infinite. Okay? So that's on this side. As we move to the right, that is pulling the spring apart. Eventually, if you keep pulling and pulling and pulling and pulling and pulling on a spring, the spring eventually snaps. And that's what happens as you move to the right. So we're pulling these things apart, moving them further and further and further. Eventually what happens is we have two hydrogen atoms that are not interacting with each other. We've broken the spring. There's no interaction between those two. So we have a compressed spring on the left, a neutral position at the bottom, and at the very, very far right is when we've stretched the spring enough that it collapses, that it breaks apart. So this is the interaction for a covalently bonded system. Now you notice that when we talked about the ionically bonded systems, we didn't have a plot. That's because it doesn't move, it doesn't act according to any sort of like mathematical equation like this. For that one, we have a different set of math equations, but you'll learn that in physics, so we're not going to cover that. So this is our interaction for this covalent bond. Well, let's take a look at the electron configuration and the orbital diagrams for this H2 molecule and see how we can get a total of 2 electrons surrounding both of them. Because if a hydrogen atom had 2 electrons, that would be a complete orbital. 1s has 2 different electrons, so that would make this hydrogen happy. So let's take H1. This is the first hydrogen. Oh, let's say HA. Electron configuration is going to be a 1s1. Orbital diagram is going to be a 1s1. Same exact thing is going to be for this HB. The second hydrogen in this system. We're going to have a 1s1. We're going to have one single box, 1s. The only way to make these happy would be to either strip off that electron, but that would leave an empty box. There's nothing below the 1s orbital. So what that means is it still wouldn't be as happy as if we put in an extra electron here. If we were able to put in an extra electron next to this, this would be a complete shell. It would be a complete set of valence electrons, 2 for the hydrogen, and the hydrogen would be happy. So what ends up happening is if we draw the Lewis symbol for hydrogen, we can draw it looking like this. This is hydrogen A, this is hydrogen B. If we move these things close enough, we end up getting hydrogens that look like this. They are sharing the 2 electrons. So the way we can look at a covalent bond is anytime we see 2 dots in between elements, we can consider that to be a shared electron. So how does this look? What does this look like? If I cover up the HB, this hydrogen looks like it has 2 electrons. That would be like saying this hydrogen looks like this. If I cover up this hydrogen looks like it has 2 electrons. They are both satisfied. They both have a completely filled valence set of valence shell electrons. We draw these 2 dots in between the hydrogens. That means they're sharing. And really, we don't normally see a covalent bond drawn like this. We generally will put a line anytime there are 2 dots in between 2 different atoms. So this is our new Lewis dot structure for hydrogen, H2. This is the introduction to Lewis dot structures. We are starting to learn how to draw these different compounds. So we know that covalent bonds act a little bit differently than ionic bonds. They don't donate electrons. This one doesn't donate the electron to this one. They both share each of their electrons, and that satisfies each of these hydrogens to think that they have a complete set of valence electrons. And we can draw the Lewis dot structure looking like this. So in class tomorrow, we're going to be working a lot of problems. Don't get confused with that plot. I just wanted to show you how it really interacts, but this is the main take-home message. You should already know how to write the Lewis or the electron configuration, the orbital diagrams, and now we can see how they can be shared. So with that, I want to say have a great night. I will see you all in class tomorrow.